Hello, and thank you for joining me today. Today we're going to look at how to solve trig equations. So I'm going to start with this little one. It's not trivial, but it's also not terribly difficult either. So there are a couple options you have. You could use sum or difference formulas, or you could go ahead and use double angle formulas. The idea behind solving trig equations is that you're going to be doing algebra mixed in with some trig identities at some point. So we're looking at this, and these are not like terms, just like we would normally do. We identify this is cosine of 2x and this is cosine of x. The 2 forces this one to be a different term, if you will, using that a little bit loosely there, than the second one. So the first thing I need to do is get to the point where all the angles are x's or all the angles are 2x's. So I'm first going to do that by looking at cosine of 2x here. And I'll notice that I have a double angle formula that tells me that I can switch that to cosine of, see here, there it is, cosine squared x minus sine squared x plus cosine x equals 0. Now some of you may be looking at that and saying, hey, he used the Pythagorean identity. Is that the same thing as cosine 2x, which means that cosine 2x equals 1? No. Pythagorean identity has a plus sign right here, not a minus. Okay, so what I did is I took all this right here and I converted it to all that right there. Okay, now the next question is, how did that help me? Maybe it did, maybe it didn't. Well, what I can do now is look for how I can start to rearrange pieces. Maybe this was not the correct path for me to go down. Maybe there was something else I could have done differently. But what we need to do now is look at how else can we start to rearrange these pieces. Look for any algebra. So the thing I see now that I can do something with is the fact that I have cosine squared x and cosine x here. So I'm just going to group those. Cosine squared x plus cosine x, and then minus sine squared x. That's equal to 0. Now, I do see something I think will be useful to us. Some of you may see it, some of you may not. Look very closely at what we got here. We have cosine squared and a cosine, and then we have sine squared. Now, a minute ago, I mentioned something about a Pythagorean identity. Well, what if I take the Pythagorean identity right here to replace sine squared x? So it's cosine squared x plus cosine x minus, now this is the funky part, okay? What goes there? Well, I know that cosine squared plus sine squared equals 1 is Pythagorean identity. So if I were to subtract cosine from both sides, I have 1 minus cosine squared x as being the leftover thing there. Now, you may say, well, what did he do? Hit pause, rewind, and do it again. I'll go ahead and say what I do is I Pythagorean my identity to replace sine squared x with 1 minus cosine negative sign right there and distribute it through to the 1 and the minus cosine. Now all of a sudden I have cosine squared x plus cosine x minus 1 plus cosine squared x equals 0. All right, now so this is what I was meaning when I said it's not trivial, but it's also not difficult. Is that I'm not really doing anything that's terribly difficult here, but there is some work involved. Now I'm just going to move this up just a little bit because we're going to need a little bit more space. So cosine squared, those are like terms, so I'm going to combine those. That's 2 cosine squared x plus cosine x minus 1 equals 0. Now a second ago, some of you were saying, well, whoa, what about that 2 way up there? Wouldn't that cause the problems? Yes, the location of the 2 did cause a problem, but this 2 is on the outside. This is a coefficient of the entire term, which is cosine squared x. There's an understood 1 right here as being the coefficient with cosine. So now what I'm really dealing with here is 2x squared plus x minus 1. I'm dealing with a quadratic. Okay, now it's not really a quadratic in the true sense of the term, but it is a quadratic trig equation. So I can, just like I can do anything else with quadratics, I can do here. I can say, well, what does this factor into? Anything that I could factor with just it being x squared and x and a negative 1, I can do the same thing with it being cosine as a result. So I'm thinking to myself, if I were to go ahead and try to factor this out, I'd say 2 times -1, which gives me -2, and all my factors of -2, which would be 1 and -2, -1 and +2. Now I'm thinking about, of those two factors, which one adds to +1? Right? Well, the second one, right? So that means I can do 2 cosine squared x plus negative cosine x plus 2 cosine x minus 1 equals 0. Some of you would be thinking, what did you do there? I took this piece right here and I turned it into those two pieces right there. Okay, I split it up. The reason I did this over here was so I knew how to split up cosine x, 1 cosine x. I split it up into minus cosine plus 2 cosine. Some of you may be tempted to go ahead and combine like terms, which actually takes us right back to where we started from, so we're not going to do that. What we're going to do instead is we're going to say, now that I have this split up like this, I can group it and factor. Now some of you just thought I said a 4-letter word there, but no, I said factor. So what's common to the two right here that I can pull out? What does everything have? Everything has a cosine. What does everything have here? Well, that's boring. Just a 1, right? Now, look. They match, don't they? Wahooey, right? So 2 cosine x minus 1 and cosine x plus 1 are my two factors. That's pretty awesome, because now I can say 2 cosine x minus 1 equals 0. Cosine x plus 1 equals 0, right? Move that up a little bit more. It's a long one, isn't it? So then I have 2 cosine x equals 1, divide both sides by 2, so it gives me cosine x equals 1/2. And then I think about my unit circle and I say, where is the angle, what angle will give us a cosine value of 1/2? Positive 1/2, right? And that location, if we're going between 0 and 2 pi, would be at pi over 3. And again in the fourth quadrant, which would be, anybody remember? Y'all aren't going to respond right now, are you? So I would do 2, it's in the fourth quadrant, it's going to be 2 times 3, which gives us 6, minus 1, which gives us 5. So it's 5 pi over 3. So those are my first two values. And I do the other one over here. So it's cosine over x, cosine of x equals -1. So that means that I'm looking for the x value where cosine's -1. That only occurs one time at pi. So my solutions here, over 3, pi, and 5 pi, oops, I forgot my pi there, over 3. Now, if we weren't in the first quadrant, or first rotation, pardon me, we would want to include some other information. Now, this is strictly if we're talking about between 0 and 2 pi, inclusively. If we're talking about all solutions, then we would rewrite this and we say that x is pi over 3 plus 2k pi, pi plus 2k pi, and 5 pi over 3 plus 2k pi, where k is just some integer, right? And what that means is that every rotation we'd come across a version of pi over 3, where pi over 3 would be the reference angle. Same thing with pi, and the same thing with 5 pi over 3. So we could go around the unit circle an infinite number of times. These are particular solutions for the first rotation between 0 and 2 pi. This is all solutions for all rotations. Okay? All right, so I'll try to create more examples. This can be kind of daunting when you first start working on it, but if you spend some time, it'll work its way out. All right, so if you haven't subscribed, go ahead and subscribe, because I like subscriptions. And go ahead and give it a thumbs up whether you liked it or not. It's a great video.